Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Hello, everyone, and welcome back. It is Thursday, February 12th, 2026. I want to start today's exploration with a feeling, a sensation that I guarantee every single one of you has felt. It's that very specific kind of annoyance. You're sitting there, maybe you're on a long video call, or you're rendering a video, or maybe you're just, scrolling on your phone with the brightness all the way up.
Yeah.
And then you feel it.
The heat.
The heat. Your phone starts to feel like a hot little brick. Your laptop fan suddenly kicks in and it sounds like a tiny jet engine is about to take off from your desk.
And your battery percentage just plummets.
It just nosedives.
Yeah.
And we treat this as normal. We just think, oh, my device is working hard. But when you really stop and think about the physics of it,
yeah,
that heat is just failure, isn't it?
It's pure failure. It is waste. In physics, we call it dissipation. And it is, without a doubt, the single biggest bottleneck in modern electronics.
So that heat is just energy that's not doing what I want it to do.
Exactly. That heat is literally your battery's precious energy being turned into useless thermal vibration. Instead of, running the app you just opened, it's just gone.
It's like paying for a gallon of gas and just pouring half of it in the ground before you even start the car. So the reason we're talking about this very fundamental problem is because of a paper that just dropped.
Just dropped.
2 days ago, February 10th, 2026, in the journal Nature Physics. It's from a team at the University of Washington, led by a researcher named Xiaodong Xu.
And it is a monster of a paper, truly.
It really is, because they are claiming to have, essentially solved the heat problem.
Yeah.
And not in some small, incremental, we made the copper wiring slightly better kind of way.
No, this is a fundamental shift.
They have engineered a material where electricity flows with zero heat loss.
Effectively zero, no dissipation. It is the first practical, verified realization of what's called a dissipationless fractional Chern insulator.
Okay, dissipationless fractional Chern insulator. That's a mouthful. I feel like we need to put a giant pin in that phrase because there is a lot of physics jargon packed into those 4 words.
There is. We'll unpack it all.
We will. But the headline, the big takeaway here, is that they have created a state of matter where electrons just flow without resistance. And this is the kicker, they've done it without the massive room-sized magnetic fields that you usually need for this kind of quantum magic.
And that is the holy grail part of this. We've known about zero resistance states for a long time, but they always required these insane lab conditions that made them totally impractical for, say, a microchip.
Right.
This paper, it completely changes the playing field.
So here's our roadmap for this analysis.
Yeah.
First, we have to start with the physics of the impossible. How do you even get electrons to stop bumping into things? We need to talk about this whole family of quantum Hall effects.
Right, the basics.
Then we need to get into the drama of the engineering. Because this isn't the first time this team has tried this. They actually took a swing at it back in 2023, and it didn't quite work.
It was a fascinating failure, though, one of those successful failures that pushes science forward.
Exactly. So we'll talk about what went wrong then, and the incredibly specific, almost artisanal changes they made to the crystal growth and this twisting mechanism to finally make it work this year.
And then there's the mystery.
Yes. We have to talk about the mystery because there's a section at the end of this paper that basically says, okay, we built it, it works perfectly, but now it's behaving in a way that makes absolutely no sense to us.
The thermal activation gap mystery. It's a genuine plot twist in the data.
So let's dive in. Section 1, the physics of the impossible. I want you to explain resistance to me like I'm, let's say a smart high school student. Why does my fan get hot? What is actually happening at the atomic level?
Okay, sure. To really get resistance, you have to visualize the life of a single electron trying to get through a wire. We have this mental picture of electricity as like water flowing smoothly through a pipe.
A nice, clean, continuous stream.
Right. But at the atomic level, a copper wire is a complete nightmare. It is a chaotic, crowded, messy obstacle course.
So the electron isn't just gliding along.
Not at all. Not even close. Imagine you're on a highway, but this highway has no lanes, no speed limit, and it's just filled with giant vibrating boulders.
Okay.
The boulders are the atoms of the copper, and the highway is also full of other cars, which are all the other electrons. So the electron hits the gas, that's the voltage you apply, and it zooms forward. But almost immediately, whack. It smacks into an impurity in the metal.
Yep.
It recovers, zooms again, whack. It hits an atom that's just vibrating because of temperature. It recovers again, whack. It collides with another electron.
And every single one of those collisions, that's the heat.
That is the heat, precisely. In physics, we call it scattering. The electron has kinetic energy of motion. When it crashes into an atom, it transfers some of that energy, making the atom vibrate even more violently.
Right.
That collective violent vibration of all the atoms is what we feel and measure as heat. So resistance is really just a measure of how often your electrons are crashing.
It's friction. It's electrical friction.
It is. It's the exact same principle. Now, for decades, physicists have been absolutely obsessed with one question. How do we stop the crashing? How can we build a highway where it's physically impossible for the electrons to hit anything?
Which sounds, well, impossible. And that brings us to the quantum Hall effect.
Okay.
I've heard this term thrown around, usually when people are talking about Nobel Prizes, but what is it actually?
Okay, so let's take that chaotic highway, your normal copper wire. The first thing we do is we cool it way, way down to near absolute zero.
So like a few degrees above the coldest possible temperature in the universe.
Exactly. That slows down the vibrating atoms. It's like clearing most of the boulders off the road. The road is now much smoother.
Okay, smooth road. But the electrons, the other cars, are still there. They can still crash into each other.
They can. So next, we turn on a magnet. And not just any magnet, a massive magnet. We're talking about magnetic fields of 10, maybe 20 Tesla. These are monsters.
Just for context, a hospital MRI machine is what, 1.5 or maybe 3 Tesla?
Right. So we were talking about fields that would, rip a metal chair across the room. It's an incredibly strong field. Now, when you apply that kind of magnetic force perpendicular to an electron's motion, the electron's path curves.
It doesn't go straight anymore.
It can't. The field forces it to move in a circle. This is a fundamental principle called cyclotron motion.
So now, instead of all the cars driving straight down the highway, they're all just driving in tiny little circles in place. That doesn't seem very useful.
In the middle of the material, what we call the bulk, yes, they're just spinning in place, completely trapped, going nowhere. But think about what happens at the very edge of the material. Think about the guardrail on the side of the highway.
Okay, so I'm an electron near the edge. I try to spin in a circle to my right, but before I can complete the circle, I hit the wall.
You hit the wall, so you bounce off it, you try to spin again, you hit the wall again, you bounce again. What ends up happening is this beautiful skipping motion. The electrons skip jump along the boundary of the material.
Okay, I can picture that.
And here is the magic part. Because the magnetic field forces everything to try and turn, let's say, to the right, all the electrons on that one edge are forced to move in exactly the same direction.
It creates a one-way street.
A perfect one-way dissipationless superhighway. There's no oncoming traffic. An electron can't scatter backwards because to do that, it would have to turn left, and the magnetic field makes that physically impossible.
So it literally can't crash.
It can't. And this is what we call a topological property.
Topology. That's the branch of math about shapes, right? The whole donut and coffee mug thing.
Exactly. In topology, a coffee mug and a donut are considered the same because they both have one hole. You can squish and stretch one into the other without tearing it. In the quantum Hall effect, the flow of electrons along the edge is protected by the topology of the system's quantum state.
So even if there's a bump, like a defect in the material,
the electron just flows smoothly around it. It can't scatter backwards. It's robust. The resistance along that edge just vanishes. It goes to zero.
wow.
And when you measure it, the Hall resistance doesn't increase smoothly. It goes up in these perfect quantized steps, like a staircase. Step 1, step 2. It's this beautiful, perfect order emerging from total chaos.
Okay, so that's the quantum Hall effect. But the paper we're discussing today, it's not just about that. It's about the fractional quantum Hall effect. And this is where my brain starts to hurt a little bit. How can you have a fraction of a step? How on earth can you have a fraction of an electron?
This is one of the coolest, most mind-bending concepts in all of physics. And you're right, an electron is a fundamental particle. It's an elementary particle. You can't take a tiny knife and slice it into thirds.
Right.
But you can get a group of electrons to act collectively as if they're fractional particles.
Okay, explain that. What does that even mean?
It all comes down to collective behavior. Think about it like this. Imagine you're in a crowded room. If everyone is just milling about randomly, you just have a collection of individuals. But what if everyone links arms and starts moving together in a very specific, complex, braided dance?
Then the crowd itself becomes a thing. The entity is the pattern of the dance, not the individual person.
That's a perfect way to put it. In the fractional quantum Hall effect, or FQHE, the conditions are so extreme the magnetic field is even stronger, the material is even cleaner, that the electrons can't ignore each other anymore. Their mutual repulsion becomes the dominant force.
There's forced to interact.
Intensely. They organize themselves into this incredibly delicate, correlated quantum liquid.
A liquid made of electrons.
A quantum liquid, yes. And the tiny ripples in this liquid, the little vortices or excitations, they behave, mathematically, exactly like particles with a fractional charge, like 1/3 of an electron's charge or 2/3.
So we're not splitting the particle. We are creating a quasi-particle out of the collective dance of the crowd.
You've nailed it. That's the term we use. These are quasi-particles. They're often called anyons. And they are incredibly important for the future of technology.
Why? Because they're stable.
Because they're topological. They're born out of this global collective dance, which makes them super robust. If you poke one individual electron, the overall dance just continues. The fractional quasi-particle remains intact.
And this is the link to quantum computing, right? This is why everyone gets so excited.
This is the holy grail of quantum computing. A normal quantum bit, a qubit, is ridiculously fragile. The slightest vibration, a little bit of heat, and the quantum information is lost. It's called decoherence.
Right.
But if you could build a qubit out of these fractional states,
It would be bulletproof.
it would be topologically protected. The idea is you could literally braid these quasi-particles around each other to perform calculations, and because the information is stored in the global topology of the braid, local noise couldn't mess it up.
So a fault-tolerant quantum computer.
The dream of a fault-tolerant quantum computer, yes.
Okay, so let's just recap the stakes here. We want this fractional quantum Hall state because it's dissipationless, no heat, and it's topologically stable, which is great for computing. But there has always been this one giant show-stopping catch.
The magnet.
The giant room-size credit card erasing magnet.
Exactly. You cannot put a 15 Tesla magnet inside your iPhone. It's just not going to happen. So for 40 years, this has been this beautiful laboratory curiosity. Look what amazing things nature can do moment, but not a let's build a product with this moment.
Which brings us to the Chern insulator. This is the proposed solution to the magnet problem, at least in theory.
In theory, yes. A Chern insulator is a type of material that, through its own internal quantum mechanics, essentially creates its own magnetic environment, the specific arrangement of the atoms and the way the electrons' wave functions interact. It generates an effective magnetic field.
So it's like virtual reality for electrons. They think they're in a massive magnetic field,
Yeah.
so they start doing the quantum Hall dance, even though there's no external magnet.
That is a fantastic analogy, yes. A property of the material's electronic structure called Berry curvature acts just like a magnetic field. So you get the protected edge states, you get the one-way superhighway, you get the zero resistance, all at zero external magnetic field.
And that's the anomalous part of the name quantum anomalous Hall effect. Anomalous because the magnet is missing.
Correct. So bringing it all back to this week's paper, Sue and his team have been chasing the ultimate prize. Not just a quantum anomalous Hall effect, but a fractional quantum anomalous Hall effect.
Right. They want the material that has the fractional charges, the 1/3 steps, and works with no magnet.
That is the goal. A dissipationless fractional Chern insulator.
And they actually tried to publish this before, didn't they? I was looking at the timeline. Back in 2023, they had a paper that claimed they found it. But looking back now, it seems like that was a close but no cigar moment.
Oh, it was a heartbreaking moment for the field, honestly. Imagine you're a scientist. You spend years designing and building this incredibly complex device. You cool it down. You measure it. And you see it. You see the plateau and the Hall resistance that screams 1/3 fractional charges here.
You pop the champagne.
You pop the champagne. But then you look at the other measurement. You measure the longitudinal resistance.
Okay, remind us again. Hall resistance is the measurement across the current, the one that gives you the nice steps. Longitudinal resistance is?
It's the resistance along the direction of the current flow. In a perfect dissipationless state, this number should be 0. A flat line at the bottom of your graph, no question.
And in their 2023 experiment?
It wasn't 0. It was something. It was small, but it was definitely measurably not 0.
So the pipe was leaky.
The pipe was leaky. Exactly. They had the right general idea. The electrons were trying to do the collective dance, but the dance floor was too messy. They were tripping. They were bumping into things. Energy was leaking out as heat. It was not dissipationless.
But I imagine for a physicist in this field, kind of dissipationless is like being kind of pregnant. It's a binary thing. It's either zero or it isn't.
Absolutely. In this game, if there's any resistance, it means the topological protection is broken. It means there are what we call dissipative channels that the electrons are finding. So for the last 3 years, the big question in the community hasn't been, is the theory wrong? The question has been, is our sample just too dirty?
Too dirty. I love that. We're talking about the most esoteric quantum mechanics imaginable, and the problem comes down to basically dirt.
Atomic scale dirt. Disorder in the crystal.
Okay, so let's move on to that. Section 3, engineering the solution. How did they clean up the dirt? Because this is where the story shifts from abstract physics to really hardcore hands-on material science.
It really does.
They used a material called molybdenum telluride, or MOTI-22. Why this particular stuff? Why not good old silicon?
Well, silicon is great for what it does, but it's electronically kind of boring for this kind of work. MOTI-22 is part of a class of materials called transition metal dechalcogenides, or TMDs. And the key thing about them is that they're layered materials, like graphite. You can literally peel them apart into sheets that are just a few atoms thick.
So they're effectively two-dimensional.
Exactly, 2D. And the real magic happens when you take 2 of these atomically thin sheets and stack them on top of each other. But you don't just stack them like 2 pieces of paper, you twist them.
This is the famous twistronics.
This is twistronics. It sounds like a 1980s dance move, but it's one of the hottest fields in physics right now. When you rotate that top layer relative to the bottom layer by a very specific tiny angle, in this case somewhere around 3 degrees, you create something called a moire pattern.
I've seen this in the real world. If you look through 2 layers of fine mesh, like 2 window screens, and you move your head, you see these weird, bigger, wavy patterns that aren't in the original mesh.
Yes, that is an optical moire pattern. In these stacked crystals, the twisting creates an electronic moire pattern. It's a giant periodic superlattice for the electrons. And this pattern fundamentally changes the energy landscape they live in. It creates what physicists call flat bands.
Okay, flat bands. This feels like a key concept we really need to nail down. What does a flat energy band do to an electron?
Right. So in a normal material, the energy band is curved. That means an electron can have a wide range of kinetic energies. It can zoom around at all different speeds.
Free to move.
It's free to move, and its kinetic energy dominates its life. It's running around so fast that it doesn't really have time to interact or care about the electron next to it.
Too busy running to chat with the neighbors.
Exactly. But in a flat band, the moire superlattice essentially traps the electrons. It dramatically quenches or flattens their kinetic energy. They slow down to a crawl. They all have roughly the same, very low energy.
Okay.
And because they aren't zooming around anymore, suddenly the most important force in their life isn't their own speed. It's the electrostatic repulsion from all their neighbors.
The chat with the neighbors becomes the loudest thing in the room.
The interaction energy becomes dominant, and that is the absolute prerequisite for the fractional quantum Hall state. You need strong interactions to force the electrons into that collective correlated dance. The twist creates the flat band, and the flat band turns on the interactions.
Okay, so they knew they needed twisted Mocol-22 back in 2023. They had that recipe.
Yeah.
So what changed between then and now? What was the big breakthrough?
It was 2 things. First, they realized their starting ingredients, the crystals themselves, just weren't good enough. Even though they looked perfect under a normal microscope, at the atomic level, they were full of defects. The dirt. So they changed the recipe for how they grew the crystals. And this is where we have to give huge credit to the materials scientists on the team, specifically Jinha Chu and a postdoc, Chao-Wei Hu. They switched to a different growth method called horizontal flux growth.
How is that different from the usual way they make these things?
Well, the more common way is something called chemical vapor transport. You basically heat up the raw powder, it turns into a gas, it drifts down a tube to a cooler spot, and it crystallizes on a surface. It's fast and it's pretty efficient, but It's a bit chaotic. Atoms can kind of slam into place. Sometimes they land in the wrong spot, creating a defect.
It sounds like the fast food version of crystal growth.
That's not a bad analogy. Horizontal flux growth is the slow-cooked, artisanal, farm-to-table version. You dissolve the raw molybdenum and tellurium powder in a molten solvent, a liquid salt called a flux. It's a big liquid bath. And then you cool that entire bath down incredibly slowly. We are talking fractions of a degree over many hours or even days.
It's like making perfectly clear ice for a fancy cocktail. If you freeze water really fast, it gets cloudy and full of imperfections. If you freeze it super, super slowly, it comes out crystal clear.
That is the perfect analogy. By cooling it so slowly, the atoms have time to find their absolute lowest energy position. They can wiggle around and slot themselves perfectly into the crystal lattice. No vacancies, no misaligned atoms. Just perfection.
And did it actually make a difference in the final product?
A monumental difference. They measured a property called charge carrier mobility, which is basically a measure of how easily electrons can move through the material without scattering. It's a proxy for crystal quality.
And
It increased by more than an order of magnitude, more than 10 times better than the crystals they were using in 2023.
wow. All from just being more patient during the growth process.
All from improving the fundamental ingredients. But that was only half the battle. You can have a perfect, flawless crystal, but you still have to perform the twist. And the act of peeling, cutting, and stacking these 3 atom-thick layers is, well, it's violent.
I can't even imagine trying to twist something that thin without getting wrinkles and folds all over it.
It's an absolute nightmare. And this was the second major problem in 2023. Twist angle disorder. Imagine you need that magic moire pattern, which requires, say, exactly 3.7 degrees of twist. But in the 2023 devices, the twist angle wasn't uniform across the whole sample. One corner might have been at 3.6 degrees, the middle at 3.7, and the other corner at 3.8.
So the flat band isn't actually flat everywhere, it's warped.
It's warped. The physics changes from one spot to the next. So an electron moving across the device hits these patches of the wrong angle and it scatters, it breaks the magic, it ruins the topological protection.
So how did they iron out the wrinkles, literally?
A student on the team, Hyun-Jun Park, gets the credit here. They refined the fabrication technique. They developed a new stamping method that uses specific polymers to handle the layers, reducing mechanical stress and ensuring the tension is perfectly uniform as the top layer is laid down.
So, okay, let's put it all together. They have the slow frozen ice, perfect crystal, and they have the perfectly ironed out uniform twist. This is the 2026 device. The moment of truth arrives.
The moment of truth. They put the new device in the cryostat. They cool it down to base temperature, just millikelvin above absolute zero. They apply the gate voltage to tune the electron density to exactly 2/3 filling.
Why 2/3 specifically?
That just happens to be one of the known sweet spots where these fractional states are predicted to be most stable. It means for every 3 units of magnetic flux in the moire superlattice, you have 2 electrons. It's a particular stable configuration for the dance.
Okay, 2/3 filling, they flip the switch, they start measuring the resistance. What happens?
The Hall resistance jumps up and forms a perfect quantized plateau, exactly where theory says the 2/3 fractional state should be. That's the good news.
Same as 2023 so far. But what about the other one? The longitudinal resistance? The heat loss?
It drops to 0.
A flat line.
A perfect flat line. It vanishes into the noise floor of their measurement equipment. In the 2023 paper, there was a clear bump, a peak of resistance there. In the 2026 paper, it is a beautiful flat line at 0.
They did it. A dissipation-less fractional Chern insulator.
They did it, and the significance of this really cannot be overstated. They have proven definitively that you do not need an external magnetic field to get this exotic quantum state. They've proven that the key variable was always material quality.
It validates the entire field of twistronics.
Completely. It shows that by engineering these moire patterns, we can create and control some of the most bizarre and wonderful phases of matter imaginable.
So if I'm a listener at home, I'm probably asking, okay, this is super cool physics, but when does this get into my laptop and stop it from burning my legs?
Well, we should be clear, there are still some major hurdles. The biggest one is temperature.
Right. This is still all happening at near absolute zero.
It is. We are not at room temperature yet. But the size of the energy gap they measured is promising. It suggests that with further improvements, we could push that operating temperature up. But the more immediate application isn't about power lines or laptops, not yet.
It's the quantum computer.
It's the quantum computer. Remember the braiding? The onions.
The topologically protected qubits.
Yes. Now that we have a physical platform where these onions demonstrably exist without needing a giant magnet, we can start to actually design circuits. You could, in principle, etch tiny pathways on this MODI-2 chip and use electric fields to shuttle these fractional quasi-particles around, braid them around each other, and perform a computation.
A computation that doesn't just collapse into dust when you look at it, funny.
Exactly. This transforms topological quantum computing from a beautiful theory on a blackboard into a tangible hardware platform. It's a chip, it exists, it's sitting in a lab in Seattle right now.
That is just incredible. But, and there's always a but in these big discovery stories, as I was reading through the notes here, there's a section labeled The Scientific Mystery.
Ah, yes, the thermal activation gap.
It sounds like the title of a Robert Ludlum thriller, The Thermal Activation Gap.
It is a thriller, at least for the condensed matter theorists, because what they found when they dug deeper into the data makes absolutely no sense based on the old rules of the game.
So, set the scene for us. They have the device, it's working, zero resistance, the champagne has been popped, and then they decide to just mess with it.
Scientists always mess with it. That's the job. They asked a very logical question. Okay, this state is perfect at zero magnetic field. But what happens if we add a small magnetic field?
Now, based on everything we just talked about with the original quantum Hall effect, the magnet is the friend. The magnet is what creates the state in the first place. So adding more magnet should make the state even stronger, right? More robust.
That is exactly the intuition everyone had. In a standard fractional quantum Hall system in, say, gallium arsenide, if you increase the magnetic field, you increase the gap.
Okay, define gap for us again quickly.
Yeah.
The thermal activation gap.
Right. Think of the gap as the width of a moat protecting a castle. Inside the castle, all the electrons are safe and sound in their perfect fractional state. Outside the moat is chaos. To destroy the state, an enemy like thermal energy has to kick an electron all the way across the moat.
So a wider moat, a larger energy gap is better.
Yeah.
It means the castle is more secure, the state is more stable.
Precisely. So they turn on the magnetic field, expecting the moat to get wider. It got narrower.
It shrank. The magnet made the state weak.
It collapsed. As they slowly cranked up the magnetic field from zero, the thermal activation gap dropped rapidly. It became easier to destroy the state. The magnet, their old friend, was actively attacking the stability of this new state.
That is completely backwards from how it's supposed to work.
It is profoundly counterintuitive. There's a line in the paper where you and the team write, "To our surprise," which is, scientist code for, "We were completely baffled and this makes no sense."
Mm-hmm.
The gap decreased quickly and then eventually plateaued at a lower value.
So what is the theory? Why? If the magnet is supposed to help, why is it hurting here?
The leading hypothesis, and it is just a hypothesis at this point, involves a kind of civil war inside the quantum state itself.
A civil war.
Yes, a competition between different quantum properties of the electrons. In these TMD materials, electrons don't just have charge and spin, up or down. They also have another property called valley.
Valley. What's that?
In the momentum energy landscape of the crystal, there are two distinct lowest energy valleys where electrons can live. They're called the K and K prime valleys. You can think of it as another quantum number, like another flavor of spin.
So electrons have spin and they have flavor.
Basically, yes. Now, the magnetic field is very good at one thing. It loves to align spin. A magnetic field wants all the electron spins to point in one direction. That's the Zeeman effect.
Okay, that makes sense. It's aligning all the little internal magnets.
Right. But the theorists think that the stability of the fractional state in this specific twisted material might depend on a very particular arrangement of the valleys. It might want the valleys to be polarized or mixed in a certain way that has nothing to do with spin.
And a magnet comes in and messes up that valley arrangement.
Exactly. The magnet storms in and says, "Attention, everyone aligned by your spin." But the delicate fractional state says, "No, wait, we need to be aligned by our valley to maintain this collective dance." The two orders are competing. The magnet is forcing the system into a spin configuration that is not the optimal configuration for the valley-based fractional state.
So the moat shrinks because the very foundation of the castle is shaking from this internal conflict.
That is a brilliant way to put it. The shrinking gap is the experimental evidence that the topology of this new state is much more complex and richer than the simple quantum Hall effect. It's born from this weird interplay of spin, valley, and the moire physics.
So does this new mystery, does it ruin the discovery at all?
Not at all. In many ways, it makes it even more exciting. It's a giant signpost that says, "New physics here." It means we don't fully understand what we've created, and that's the best place to be in science.
It's not a bug, it's a feature.
It's a new discovery that's come along for the ride. It gives us a new knob to turn and a new puzzle to solve.
This brings us to the final section, the future outlook. Xiaodong Xu seems incredibly optimistic in the paper's conclusion. He has this great quote: "The quantum Hall community has made repeated breakthroughs by improving sample quality over the last 40 years.
That's the clean lens philosophy of science.
Explain what you mean by that.
Think of early astronomers looking at the sky through a dirty, low-quality telescope. You see a faint, fuzzy blur. You might think that blur is a single star, but then you spend years grinding a better lens, making it cleaner and more perfect.
Okay.
You look through the new, clean lens and you realize that blur wasn't a star at all. It was an entire galaxy. Or it was binary star system. The dirt in your instrument was hiding the true, more complex reality.
The dirt hides the details."
For 40 years, the atomic-scale dirt and disorder in our materials has been hiding the true, bizarre nature of interacting electrons. As we clean the lens with these incredible techniques like horizontal flux growth and low disorder fabrication, we aren't just making things more efficient, we are revealing new laws of physics that were hidden in the noise.
Zhu follows that up by saying, "We hope that the progress on this new platform will be even faster."
And I think he's right to be optimistic, because now we have a recipe. It's not a mystery anymore. We know the key ingredients: high-purity Moti-22, the flux growth method, the low disorder twist. Any lab in the world with the right equipment can now start making these high-quality devices and exploring.
So the floodgates are about to open.
People can try different twist angles, different layer combinations, different TMD materials. It really feels like we are standing on the beach of a new continent, and we've just figured out how to build the boats.
I want to circle all the way back to where we started this conversation. That hot phone in your pocket, that roaring data center.
The radiator world we live in.
It really feels like we are living in the steam age of computing. It's loud, it's hot, it's incredibly inefficient.
We absolutely are. We are brute forcing electrons through solid rock and just dealing with the heat as a waste product.
And this research, this dissipationless fractional Chern insulator, this feels like the first real glimpse of the solid-state, silent electric future.
It is. It's a future where electrical current flows like a superfluid, where heat becomes an engineering choice, not an inevitable byproduct, where quantum information isn't stored on a material, but is braided into the very fabric of the material itself.
It's just mind-blowing stuff. And the fact that this is happening now in 2026 makes me incredibly excited to see what the landscape looks like by 2030.
The pace of discovery here is just breathtaking.
I think I want to leave our listener with one final thought to mull over. We often look for the next big thing in a new app or a new gadget design. But sometimes, the biggest revolutions are completely invisible. They're happening at the atomic scale, inside a tiny flake of crystal that has been twisted just right.
The twist is the key.
Thank you so much for walking us through this. I feel like I finally actually understand what a Chern insulator is.
It was my absolute pleasure. This is the kind of stuff that makes being a physicist fun.
And to everyone listening, thank you for being part of this exploration. Keep your devices cool, stay curious, and we will see you in the next deep dive.